All right, boys and girls. Well, welcome back to Valley West High School, CP chemistry class. The last assignment that I gave to you was in regards to a topic called periodic trends, and so we're going to pick up right where we left off. And what I did for today is I published to Google Classroom a list of 18 questions, and what I'd like to do is go through a few of them with you, sort of get your mental juices flowing again, and I'll just allow you to finish those up for tomorrow, and that's that. As you can see on the screen, here's a copy of the questions that I had published. You either could just print them out or maybe write them down if you don't have a printer at home. All right. Over here on my little webcam screen, I have a periodic table written out here. And what we're going to do is just go through the basic trends in this periodic table as it relates to things like electronegativity, atomic size, ionic size, and things of that sort. So let's just go ahead and take a look at problem number 1. It says, based on their positions in the periodic table, predict the smallest atomic radius. And that would be between, or taking into consideration, magnesium, strontium, silicon, chlorine, and iodine. So if we go here to our periodic table, what is our trend in atomic radii, or the size of an atom? Now, as we go down the periodic table, as we go down groups, the atoms get larger. And it's a reasonably easy explanation. As we go down, each new period adds a new principal energy level to the electrons surrounding that nucleus. So, for example, hydrogen and helium, which is period 1, has electrons in the n=1 shell only. The next period 2, lithium through neon, all the outer electrons, or the valence electrons, are in the n=2 energy level. Period 3, sodium through magnesium, or sodium through argon, all the outer or valence electrons are in the n=3 energy level. And this is the 4th and the 5th, 6th, and 7th. And since we're getting further and further away from the nucleus, we expect the atom to get larger and larger. Right? Now, this next trend, as we go from right to left through the periodic table, atoms get bigger going this way. So, in effect, something like helium is smaller than hydrogen. Hydrogen is a bigger atom than helium. Lithium through neon. Neon is the smallest in that period, and lithium is the biggest. Right, so we are becoming larger going that way and larger going this way. And what we're talking about here is atomic size, or atomic radii is typically how it's phrased. Okay, so let's take a look at the elements that we're dealing with here. So we'll bring a periodic table here. Let me see if I can't mark these off here. So first one is magnesium. So that's this guy right here. Put a little highlight over that, and then strontium, which is below it. So strontium's lower, it's going to be bigger than magnesium. We have silicon. Now silicon's over here. Now things further to the right hand side are going to be smaller. So silicon's smaller than magnesium, right? And then we have chlorine, which is even further to the right, that's even smaller still. And then we have iodine, which is here. Okay. So we want to, the question is, based on the position, which has the smallest radius? Oh, it's got to be chlorine. Chlorine's got to be the smallest, right? This guy right here. Why is chlorine the smallest? Chlorine is the smallest because it's furthest to the right and highest on the periodic table. If we go back to our periodic table here, the trend is larger going that way and down. So I guess you could say going in a diagonal, we're getting larger. So that means if we're going in a diagonal in the other way, this way, we're getting smaller. So anything that's in the upper or closest to the upper right-hand corner of the periodic table would be the smaller, smallest element. And that, again, was chlorine. All right. Let's take a look at, let's see, number 2 is pretty much the same question, except now it's looking for not the smallest but the largest. I'll let you deal with that one. How about number 3? Based on the position, predict which has the largest first ionization energy. All right, well, let's see if we remember, first of all, what ionization energy means. All right, if we have some element, let's say sodium, all right, if we apply enough energy to that sodium atom, we could rip an electron off of it. Right? Now, once sodium is minus that electron, it becomes a positive ion, right, or a cation. So a sodium atom becomes a sodium ion when we remove an electron. And this takes a certain amount of energy. We call this an ionization energy. Right? Now, the ionization energies of the elements vary in a very predictable way. All right? If we look at our periodic table, our ionization energies get bigger or larger as we go from left to right. Larger ionization energies, meaning it gets harder and harder to remove electrons from elements that are further to the right-hand side of the periodic table. The ionization energies also increase as we go up the periodic table. Larger ionization energies this way. Right? So it's harder to remove an electron from hydrogen than it is from something like francium. Or put another way, to remove an outer electron from francium is easy compared to removing it from hydrogen. Right? So as we go from the bottom left corner, we get elements that are very easy to remove electrons. And as we go into the upper right-hand corner, it becomes harder and harder to remove those electrons. Okay, so if we go ahead and look at our periodic table again, let's see if we can't figure this part out. So the elements in question here are magnesium, so I'll highlight, we don't want that. So we'll highlight magnesium is the first one, and then barium. Barium's down here. Right, barium's further down, so it's easier to remove electrons from barium, right? And then we have boron. Boron's over here. Boron's further to the right, so it's harder to remove electrons from boron, right? And let's see, and oxygen. Right here. So those 4, magnesium, barium, boron, and oxygen. We want to know which one has the largest first ionization energy. First ionization energy is just the amount of energy required to remove the first electron. There are others. A second ionization energy, if we wanted to remove a second electron, we'd have to add an ionization energy there. We call it the second ionization. And there's also a third ionization energy. That's to remove the third electron. But we're talking only the first here. All right, so when we look at magnesium, barium, boron, and oxygen, oxygen is the higher up on the periodic table and the furthest to the right. So what would be oxygen, in fact, that would have the highest ionization energy here. It's harder to remove an electron from oxygen than it is to remove electrons from the other elements here, boron, magnesium, and barium. All right. Number 4 is very much the same as number 3, except they want not the largest first ionization, but the smallest. So you just have to look for the element that's what? Lowest on the periodic table and furthest to the left. And number 5, based on their positions, rank the following atoms in order of increasing first. That's pretty much the same. You can do that. Same with number 6. Number 7 is an interesting question here. Atoms of which group in the periodic table have a valence shell electron configuration of ns2np3, where n is the period number of the element. N is just the principal energy level, or the principal quantum number. So it could be 1s2, or 2s2, 2p3, 3s2, 3p3. These all are going to fall within the same group on the periodic table. All right, if we go and we look at a periodic table, let's see, we could do it this way. All right, all the elements here in group 1A, hydrogen down through francium, have just a single outer electron, so their electron configuration is going to end with something S1. Hydrogen's 1s1, lithium's 2s1, sodium's 3s1. The next column is going to end in S2. Beryllium is 2s2, magnesium is 3s2, calcium is 4s2. Now we jump over the center of the periodic table, the transition metals, and we bump over to the group 13 or group 3A, and that includes elements whose last configuration is S2P1, and then carbon would be S2P2, nitrogen S2P3, and in fact that's exactly the place we want to go to in order to answer number 7. What elements or what group of elements have an electron configuration that ends in S2P3? That's this group right here. Nitrogen would end in 2s2, 2p3. Phosphorus would be 3s2, 3p3. Arsenic would be 4s2, 4p3, etc., all the way down. So that would be the answer to that one. And that's more of a question from last chapter than this. Although the electron configurations are certainly a periodic function of the location of the element on the periodic table. All right. Well, I'm going to stop this video right here so that we can break this up a bit, and we'll make another short one to go over some of the other problems.